Here we look at the symbol description language, or SDL file, used to create the symbols for the Arria10 GX160 device in detail. We show the lines of SDL that define each symbol alongside the symbols they created to demonstrate the way SDL works. All lines that start with the hashtag are comments and are ignored by Part Builder. Any text appearing after a hashtag on a symbol line is also a comment and is ignored. When SmartFrac creates the SDL template files, it includes this cheat sheet section of comments describing the elements of the SDL language at the beginning of the file. A symbol start directive looks like the symbol name equals statement, where the actual symbol name we want to appear on the symbol is inserted for the symbol name. The symbol end directive is a semicolon at the start of a line. In between the symbol start and end directives are a collection of comments, pin match statements with pin modifiers, and spacer commands. The GXB Exceivers section contains the power and special resistor reference pins, the clock reference pins, and the transceiver input and output diff pairs for the two GXB banks, 1D and 1C, in the device. The GXB section starts with the GXB Exceivers equals line and ends with the semicolon at the bottom. The pin matches start with the right equals VCCH GXBL, which tells Part Builder to place any pin matching VCCH_GXBL on the right-hand side. Part Builder finds and places the two VCCH_GXBL pins. The left equals RFTL places the single RFTL on the top left. The balance sim sides +1 command starts a new location for the left and right pins, one pin below the last pin location found on either the left or the right side. In this case, it was the second VCCH pin on the right. The VCCR, GXB-L1D, and VCCT GXB-1LD power pins are next on the left and right, followed by a balanced sim sides +2, which moves the next group of pins step 2 below the lowest pin on either side. That gives extra room to fit decoupling caps in the schematic. The left D pair equals ref clock GXB-L1D_CHTP places the PN pins of the diff pair on the left side and automatically puts a spacer underneath the N pin. Another balanced sim size +1 pushes the next group of pins down by one more spacer. The left D pair equals GXB-L1D RXCH5 to 0P places the 6 diff pair inputs with P and N placed together on the left side, with CH5 at the top and CH0 at the bottom. Part Builder automatically adds a spacer between each of the diff pairs. The right D pair equals GXB-L1D_TX_CH5 to 0P does the equivalent for the 6 TX pairs on the right side. Next is the CHB ref clock diff pair with the balanced sim size +1, and then we repeat the whole set of match statements for the 1C power pins, ref clocks, and input-output pins. We finish up with the RREF_BL on the bottom left. The IO3V bank 2L symbol contains all the pins for the 3-volt IO bank numbered 2L. We can see that the IO3V bank_2L name is displayed at the bottom of the symbol. The symbol starts with the IO 3-volt bank_2L equals statement and ends with the semicolon 7 lines down. The first pin matches the left equals VCCIO2L_. Part Builder finds the 3 VCCIO2L pins and places them on the left. The balanced sim size +3 moves the next group of pins down 3 spacers, again leaving room to add decoupling caps in the schematic. If you needed more room, you could change it to +4 or +5. The left equals arrow VREFB_N0_2L places the 1 VREF_N0_2L pin on the left side, and then the balanced sim size +1 starts a new section for the pins in the part. The left equals I_OP_.*2L is a powerful regular expression that tells Part Builder to find any pins that starts with I. The square bracket OP says to look next only for an O or a P, and we only have the O's in this case. The .*? Looks for any sequence of characters, and then the pin must end in an _2L. This regular expression matches all 48 pins in the 2L IO bank, and since Part Builder is going through the pin list in the order it was sorted when it read the Arria pin report, it places all the IO pins from IO48_1N_2L down to IO024P_2L in order on the left-hand side. The SDL for the IO bank's 2K2J symbol is very similar to the previous SDL for the IO bank 2L, but it places the IO bank 2K pins on the left and then adds the 2J pins on the right. To keep the pins balanced, we add the VCCIO2K and VCCIO2J matches on the left and right. We use the balanced sim size +3 to make room for the decoupling caps. We then add the VREF N02K and VREF N02J on the left and right, and use a balanced sim size +1 to separate them from the next group, which will be the IO pins. The IO pins use the same powerful regular expression I square bracket OP square bracket $*?, only with _2K and _2J at the end instead of _2L from before. This will match all the IO bank 2K pins and put them on the left, and the IO bank 2J pins on the right. Again, the pins will be placed in the proper order from IO47 down to IO0 on each side. The IO bank's 2A_3A is the same as the _2K2J symbol, with 2A substituted for 2K and 3A substituted for 2J in the symbol name and pin match statements. And we end up with all the bank 2A pins on the left and all the 3A IO bank pins on the right. The config ADC block contains a lot of differently named pins, so there are more pin matches in this block than most of the other blocks. We separate the analog inputs pin section with VREF on the left and temp diode on the right. The VSIG 1 to 0 diff pair statements places 2 diff pairs, and then we finish with ADC ground on the left. We use a balanced sim sides to start a new section for the config pins. We add confdone and nstatus on the right, and nconfig and nio pull-up on the left. We add a left spacer and then the 3 mselect pins using mselect 2 to 0 on the left. We start a new section with the balanced sim sides, add declock on the left, and the AS data 3 to 0 pins go on the right. We add a balanced sim side using the BSS abbreviation, and we add NCE on the left and 3 NCSO pins on the right. We add a balanced sim sides to start a new section and then place the JTAG pins. The power symbol 1 symbol starts with VCC on the left. All 48 pins will be placed here. So then we distribute the other power pins on the right using right equal spacer and right equal spacer 2 to 0 to break the power pins up. The ground symbol is interesting because it has so many pins. We use both equals ground to place the 184 ground pins equally on both sides of the part. Here we look at the configuration setting and notice that the max sec pin count was set to 158. So when Part Builder gets to the 159th ground pin, it knows it should create another symbol to stay within the limit, and it places the remaining 26 pins on the ground_1 symbol. So we can place all the ground pins with this one simple both equals ground statement. For the NC, D, and U symbol, we place the D and U pins on the left. We start a new section with the balanced sim sides +2, and then we place all the NC pins on both sides using the both equals NC command. The last picture shows how we could have used a loop to create the same 3 symbols for the 2L, 2K2J, and 2A3A GPIO symbols. When Part Builder sees the tick4 LB, RB statement, it knows it should expand the loop, and it goes through the list provided and pulls out 2 items at a time, one for the LB and one for the RB. The first pair is 2L and bang undef. Bang undef tells Part Builder to ignore those matches, so it will build the first symbol only for 2L. The next pair will be 2K and 2J, and the next pair will be 2A and 3A. Shown below the loop statement is the SDL after Part Builder expands it. It creates the 3 symbols by substituting in the values for the tick LB : and the tick RB variables, and we can see the same 3 resulting symbols on the right. If we had 10 more IO bank pairs, we would just add their IDs to the list following in the for LB RB statement, and Part Builder would build 5 more symbols for us with the same loop.